Hello everyone. I'm going to be working on a quick final review with you guys. I'm going to start off with ionic and covalent, and then we'll go ahead and we'll work on the final from there. Okay, so we're going to go ahead and we're going to start with ionic bonds. And you have to remember that ionic bonds are between one metal and one non-metal. So that is the way that you will be able to distinguish if you have an ionic bond. So things that you guys are going to go ahead and things that you're going to see. First of all, you have to be able to distinguish your metals and your non-metals on the periodic table, right? This zigzag line is where we go ahead and where we distinguish our metals from our non-metals, right? So anything that is in here plus the stuff that we have plus hydrogen, right? Those are all non-metals. So if you guys look at these, a lot of them are gases, right? Some of them are liquids, right? But they are all non-metals. And then everything that is going ahead and everything that is to the left of that, so pretty much the rest of this table that we have all in here, right? These are going to be all of your metals. So when they ask you to go ahead and to distinguish, oh, is something an ionic bond or something's a covalent bond, you need to go ahead and you need to find the location of your metals and your non-metals. Very commonly for ionic bonds, you are going to go ahead and you're going to see ionic bonds between these guys right here and these ones right here. Those are one very common pair of an ionic bond. And then another common pair that you guys will see is these guys here with these ones here. Now, those are perfect matches. You have to remember that you can also have an imperfect match, which means that you can have either more metals or more non-metals. But for the most part, during the final, the thing that they want you to be able to go ahead and to recognize is if it is an ionic bond or not, and what is happening during an ionic bond. Okay, so we're going to go ahead and we're going to do an example together with our ionic bond so that we can go ahead and we can look at some of the rest of the properties. So I'm going to do an imperfect share. I'm going to go magnesium and chlorine. Now, I'm going to do magnesium chloride. Things that I do have to know to go ahead and to draw this out. Number one, I have to go ahead and I have to know my Lewis dot structure. So for my Lewis dot, right, all that I have to do is I have to go ahead and I have to write down the symbol. So I already did that, right? Then I have to figure out how many valence electrons do each of these things have. Right, so for valence electron numbers, I know that this whole column has 1, this whole column has 2, this is 3, 4, 5, 6, 7, and 8. The exception right here is helium. Helium has 2 valence electrons. Okay, so for my magnesium, I go ahead and find my magnesium. I see that it's with the number 2 on top, right, of that column. So I'm going to draw 2. Chlorine, I go ahead and I look at chlorine and I have 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Right, so I'm going to go ahead, I'm going to draw an arrow to go ahead and to represent this transfer. So an arrow here to go ahead and to represent that transfer, right? And I have to remember that I have 2 rules. My first rule is that my metal needs to get rid of all electrons. Right, and my non-metal, we're going to go ahead and we're going to get to 8 valence. So, I'll see on here that my chlorine now has 8. It can't take any more. So what I'm going to do is that I'm going to have to go ahead and I'm going to have to draw in another chlorine And this chlorine is going to go ahead, and this chlorine is going to take the last electron on there. So what I end up with is I have an Mg and I have a Cl. Each of my chlorines have a negative charge, and again, this negative charge means that I took one electron. Now, if this atom took on 2, it would be 2 minus. If I took on 3, it'd be 3 minus. But either way, it took on an electron. Chemistry, we don't write 1, so that is what we see on there. And then I'm going to go ahead, I'm going to write this 2 at the bottom. This 2 at the bottom means that I have 2 atoms. This means 2 chlorine atoms. Now, for magnesium, right, it is 2 plus, right? And magnesium is 2 plus because it gave 2 electrons. Right, so what you're going to also see on here with ionic bonds is that we're going to have opposite charges attract. And we're going to go ahead and we're going to see that my charges do balance out, and I have my ionic bond. Now, covalent bonds are a little bit different, but we still have some rules that go ahead and that apply to a covalent bond. My covalent bonds are 2 nonmetals. Right, and in this case, instead of like getting rid of electrons and all of that, my rule in this case is that I'm going to make sure that all atoms have 8 valence. And the only exception to this rule is hydrogen. Hydrogen needs only 2 valence electrons to go ahead and to be satisfied on there, because hydrogen wants to be just like helium, 2 valence electrons. So an example that I can have on here, I'm going to start off with the nitrogen. So same thing, I'm going to start off with the nitrogen. Nitrogen, if I look on here, this is where it is on the periodic table. There's a 5 on the top, which means I have 5 valence electrons. Right, then I can go ahead and I can do another oxygen right here. And oxygen has 6 valence electrons. I'm going to do another oxygen right here. And again, another 6 valence electrons, and then I'll just do a hydrogen just to show you guys how this works. Okay, so what I'm doing on this thing is that I'm going to go ahead and I'm going to connect dots or connect electrons to represent sharing. Right, so I'm going to go ahead and I'm going to show that, okay, these 2 are going to share, these ones are going to be shared. This is going to get shared, and this is going to get shared. So I can go ahead and I can have an example of the sharing that can occur. So to double check if this is correct, right, all I would have to do is that I would go ahead and I would count these off, and the bond counts as 1. So I see that that oxygen has 8. This also has 8. This has 8, and then hydrogen just needs 2, so 1 and 2, and I'm good. So I can see that, okay, this is a perfectly good covalent bond that I would have. And again, the big thing that you're looking for in these ones is 2 nonmetals. So make sure that you are able to recognize that these are nonmetals that are going ahead and that are bonding. Right, and this is all about going ahead and making sure that these atoms are stable. Having 8 valence electrons makes an atom stable. Okay. So those are your big topics, ionic and covalent. Now we're going to go ahead and we're going to review some other topics that you guys will see appear on the final that has to do with atoms and trends and all of that. So we're going to start off with just some atoms. I'm going to start off with isotope notation because that is one of the things that people struggle with. Isotope notation, ion notation, you guys will see that very similar stuff. So I'm going to do an arsenic one. So I have arsenic. I'm going to say that my arsenic weighs 75, and it is a 33 on here. We'll go a 3 minus charge in this case. Okay, so what's going to happen? Right, things that you guys should know. Right, first of all, know that this is a mass number. So this is mass number. This is atomic number. Right, this is my charge, obviously. Right, so to go ahead and to figure out my number of protons, right, it's just my atomic number, and that is going to be 33 in this case. Neutrons, we're going to go mass number minus atomic number. Right, so I'm going to go 75 minus 33. Right, and if I go ahead and if I do that, 42. Right, electrons. Now, depending on the charge, you can go ahead and you can have two formulas. I'm going to take my atomic number, which should be my number of protons, and I'm going to either plus or minus the charge. Right? So, if it has a negative charge, and a negative charge is called an anion, which is the case in this one, I'm going to go atomic number plus the charge, because that means that I'm adding in more electrons. If I have a cation, is going to be the atomic number minus the charge, because again, I want more protons, so I'm going to have less electrons. Right, so it's going to be up to you to figure out which one you're going to use. If it is neutral, which means that we have no charge, it's just going to be equal to my atomic number. So in this case, right, I have a negative charge. So I'm going to go with 33 plus 3, which will be 36 in this case. So those are going to be the totals that I have on there. And again, those are some of the things that I don't want you guys to get hung up on. So please make sure that you guys know that. All right, so then from there, we can kind of expand on this and we can talk about how we would express these charges and all of that. So if I had this ion, right, and if I were to draw this great big Bohr model, and I could go ahead and I can express that -3 charge by making sure that I have 36 electrons. So that would mean that on the outside, right, my arsenic would have 36 electrons on the outside. If I were to go ahead and if I were to do a Lewis dot structure, right, and this is the Lewis dot structure of an arsenic 3-. So if I'm going to have a Lewis dot structure of a 3- charge, right, what I'm going to have is a 3- charge means that I have 3 extra electrons for this arsenic, right? A regular arsenic, right, would mean that I have 3, right? 1, 2, and 3. Hold up. Arsenic, 5. Sorry, 5. Arsenic has 5 valence electrons. Usually has 5. Right, in this case, I'm a 3- charge, which means I have 3 extra electrons. So now, if I'm using a 3- charge, my arsenic is going to have 6 valence electrons. So just keep that in mind. If they go ahead and if you're bonding, if you're going ahead and if you're talking about, okay, if it's ionic or covalent, right, make sure that you guys know that if you have a charge, very likely that it's ionic. If you are adding in those extra electrons, that goes ahead and that helps it add electrons on that Lewis dot structure. Okay. So we're gonna go ahead and we're gonna expand on this, and we're gonna go ahead and we're gonna do a short Bohr model together. So if we have a Bohr model, and you guys will see, I think just one of these. I don't think there's too many of these. Okay, so if I do a Bohr model, I'm gonna do something small. I'm gonna do fluorine. Fluorine is I'm gonna say my fluorine is 20. And I have a 9 right there. And I'm going to go a -1 charge so that you guys can see what's happening. Okay, so like we mentioned above, right, for protons, I'm going to have 9 because that's my atomic number at the bottom. Neutrons, I'm going to go 20 minus 9, right, which should be 11. And then electrons, in this case, I'm going to go my protons. If it's a negative charge, I'm going to add. So 9 plus 1, and I'm going to have 10 electrons on here. So for this Bohr model, I'm going to go my Bohr model in this one. I have 9 protons. Neutrons is going to be equal to 11. First ring holds 2 valence electrons. So I'm going to go, not valence, but just regular electrons. 2 electrons in that first ring. All right, next ring goes ahead and holds up to 8. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have now 10 electrons on here. So remember, when it has a charge, make sure that this number matches. That's a really common mistake that I've been seeing with students, is that the number of they write the right number of electrons, but they don't necessarily draw it. So make sure that you do draw the correct number of electrons on there. Okay, and again, the closer you are to A to the valence, the more stable you are. Okay, so next thing is going to be our trends. We are going to go ahead and we're going to be looking at my periodic table one more time to go ahead and to note some trends. So there are 3 trends that we're going to go ahead and that we're going to talk about. Our first one is atomic radius. And the correct definition is, the spacing between the 2 nucleuses of half of the space between the 2 nucleuses of the atom. But if you just take radius for what it means, face value, right? It's basically like half the diameter of an actual atom itself, right? Which basically boils down to how big the atom is. Right? So the radius basically asks, okay, how big? Which one is your biggest? Right? So your biggest one on the periodic table is going to be francium right here. So as we go ahead and as we go this way and as we go that way, right, we have an increase in how big these atoms are. So that's what we talk about with atomic radius. Then we're going to go ahead and we're going to move into the other 2 trends. My other trend is electronegativity and ionization energy. They both go the same way. So I'm going to draw both of the arrows, and then I'm going to explain what the differences are. Okay. So electronegativity, ionization energy, both go the same way. So you guys will see that it goes up towards this. Okay, so if we're going ahead and if we're doing definitions. Okay, so if you go ahead and if you look at these two definitions, electronegativity is how much you want an extra electron, right? So there are a few atoms on the periodic table that want that extra electron, namely fluorine. Fluorine is going to be the one that's going to be, okay, I want that extra electron, right? They will do whatever it takes to go ahead and to have that extra electron. Ionization energy is a little bit different. Ionization energy, we're looking at energy cost to go ahead and to pluck off an electron. So if I were to go ahead and if I were to take an extra electron away, right, I'm going to look at, okay, what's going to cost me the most to go ahead and to start plucking off electrons. And you'll see it's up in that corner with helium, right? So you will see that helium and the noble gases do count in this ionization energy trend. In electronegativity, though, things to keep in mind is that your noble gases do not count in electronegativity. So in electronegativity, none of those guys count, right? Ionization energy, atomic radius, they do, right? Electronegativity is the only one that doesn't. Because if you look at this definition, it's you want an extra electron, right? Helium, neon, argon, all of those atoms, they already have A valence electrons. They're already stable. They don't need an extra electron. So they are going to be discounted from the trend and put back in the back of that trend. So here's what we're going to do. I'm going to go ahead and I'm going to circle a few elements on the periodic table. And we are going to go ahead and we're going to organize them based off of each of these trends. We're going to organize the same few just so we can go ahead and we can kind of see, right, what are some of the trends that we have happening. Let's do neon. Okay, so we're going to go in and we're going to start with radius. We're going to look at how big it is. Right, so when I compare all the ones that I have in orange, I'm looking for, okay, which one is closest to francium? So my biggest one, so I'm going to organize from big to small. I'm going to go with barium first because barium's closest. Then I'm going to go with manganese. And again, this is just strictly based off of position on the periodic table. Then I'm going to go with phosphorus. Right. Then I'm going to go oxygen and neon. Right. So that is going to be how I'm going to go ahead and how I'm going to organize my atomic radius. And again, by position only. Right. Then I'm going to do the same thing with electronegativity. Right, so electronegativity, I'm going to go fluorine and neon, right, and I'm going to look at how much I want that extra electron. Very easy choice here. For fluorine, I'm going to see that, okay, my fluorine, oxygen and neon are like at the same spot, but my neon doesn't count for electronegativity. So I'm going to say that oxygen has the greatest, right? Then I'm going to go phosphorus. Then I'm going to go manganese and barium. And then I'm going to put neon at the end, right? Because neon is a noble gas. It does not count in this trend. Then if I go ionization energy, a little bit different, right? I'm going to go ahead. I'm going to put neon first because neon is now closest to helium because that's what I'm looking for in ionization energy. Then I'm going to go oxygen, phosphorus, manganese, barium. So that is how I would organize those things based off of trends. Again, position on the periodic table. Know that electronegativity does not count noble gases. So noble gases automatically kick it back over to the end. So those are going to be the things that you guys will see on there. And you guys will see a few of those types of questions. So now that we covered this, we're going to go ahead and we're going to backtrack even further into some energy stuff that we went into at the beginning of the year. So we're going to go ahead and we're going to talk about energy. And I'm going to start with the three types of heat transfer: convection, conduction, and radiation. Okay, so convection. Convection is a cycle, and you should have the heat rises, cold sinks, and it is all based off of density. So you see this cycle that happens. Very common in like stuff that's boiling. It happens in fluids, which includes liquids and gases. So this is where you guys will see this the most. Liquids and gases, you guys will see convection. So what's going to happen is that we're going to have some sort of heat source. It can be a fire. It can be the sun, whatever that heat source is. Right, and that heat source is going to go ahead and it's going to separate out these molecules a bit. And they become so spread out that they become less dense. And because they are less dense, these molecules are going to rise. So you go ahead and you see that, right? They go ahead and they rise toward the top, right? They become so warm, they go ahead and they become less dense, they rise. Right, then once they get to the top, what's going to happen is that these molecules are going to go ahead and they're going to be cooled down. And when they cool, they're going to become a lot more tightly packed. So they cool at the top and they're going to become more dense. And they're going to sink. So this cooler stuff is going to go ahead and it's going to become more dense. It's going to go ahead and it's going to sink to the bottom, right? And then it goes ahead and hits the heat source again. Once it hits the heat source again, it goes ahead and starts the cycle over again, right? Next one is conduction, and this is going to be heat transfer by touch. Right, so what is going to happen is that warm molecules, same as we kind of saw on convection, the warm molecules become more spread out. And because they are more spread out, they're kind of bouncing around. They have more energy. Whoa. And what they're going to do is that they're going to transfer this energy to more compact molecules. If I were to go ahead and if I were to diagram all of this, right, this would be my cold area, this would be my hot area, and this would probably be warm. Right, so these hot molecules are going to go ahead and they're going to hit the warm molecules. They get the warm molecules more excited, more moving, right? And then they're going to hit the cold molecules. They're going to go ahead and they're going to try to get the cold molecules moving a little bit more. So they're going ahead and they're passing that energy by directly touching these molecules, right? This is where we get the word good conductors from, is this heat transfer by touch, right? And this is going to continue as long as something is touching it. And they're going to go ahead and it's going to continue until we reach equal temperatures. So that is that second law of thermodynamics. For this one, I should note that it continues. Right, radiation, right, is heat transfer by waves. Right, so the sun is a great example, right? You'll notice that in convection, conduction, you got to be right next to that heat source, literally almost on top of it, right? Radiation is that transfer through waves, right? So the waves go ahead and the waves excite those molecules. And again, a faster molecule is a warmer molecule. So, again, I can go like something that is cold, is going to tend to be tightly packed and more dense, right? Something that is hot is going to be more spread out and less dense, right? So you'll see that there's a connection between density and temperature, and that's very often what you guys will see in convection, conduction, radiation. All right, so those are a couple of things on there. Okay, so two more topics. We got to expand on density and Q equals mc delta T. All right, so density. Density is mass per unit volume, right? So you get this formula, D is equal to M over V, right? So how much mass you have in a certain amount of space, right? So like I mentioned over here, right, this is more dense because I have more molecules here. This is less dense because I have less molecules there, and I'm assuming that I'm going in the same space. I can also calculate this out, right? Density, if I went ahead and if I did this, this is grams over milliliters. Mass is going to be in grams and volume is going to be in milliliters. All right, so if I had something that is per se 5 grams, if I had per se 5 grams of salt and 52 milliliters of water, right, what I'm going to go ahead and what I'm going to do is I'm going to go 5 over 52, and then I just simply divide it. If you're putting it in your calculator, remember that the number 5 goes in first, then you go ahead and you divide it by 52, and I would get 0.096. Now, if I had another one, let's say 7 grams, right, I can do the same thing. I can go 7 over 35. That should be 5. 0.2. Whoopsies. 0.2 grams per milliliter. Sorry for neglected to write my units. Right. I can go ahead and I can look at this number and I can go ahead and I can compare them. So if I had these two solutions and if I were to go ahead and if I were to do like some sort of density column, like you did in your lab earlier this year, I can organize them by where they would be. So I have to remember that something more dense is going to sink. Something that is less dense is going to float. So if I had these two solutions, my one that's going to be on the bottom is this 0.02 grams per milliliter. My one that's going to be on the top is that 0.96 grams per milliliter. So that is what you guys will see there. Okay, so last thing that we have to go over is Q equals mc delta T. So we're going to go over the variables first. So this is heat in joules. This is mass in grams. And then delta T is the change in temperature. And this is specific heat. And they'll usually give you a value, and it depends on what it is, and that's joules over grams degrees Celsius. Okay, so in this, we're going to go ahead and we're going to do a sample problem real quick. So if per se I am calculating the heat in joules, I'm going to go ahead and I'm going to say my solution I have 100 grams of whatever it is, right? And then that specific heat is 4.186 joules over grams degrees Celsius, and that's the specific heat of water. So if it's water, you're going to see that number. And then you're going to see a change in temperature. So sometimes they'll give me two temperatures. If I have a starting temperature of, let's say, 50 degrees Celsius, and I have an ending temperature of 100 degrees Celsius, right? I'm going to go ahead and I'm going to see what I have on there. So I would have to go ahead and I have to figure out my delta T, which is final temperature minus initial temperature. So my final temperature in this case is 100 minus my initial temperature, which is 50, right? So my delta T is going to be equal to 50 degrees Celsius, right? So now I'm ready to go ahead and to plug this in. So I'm going to go ahead, I'm going to rewrite my Q equals MC delta T, right? I'm going to go ahead, I'm looking for Q, right? I have an M, which is going to be 100 grams of my water. My C, which is 4.186 joules over grams degrees Celsius. And then my delta T in this case, which is my final minus my initial, right, which is 50 degrees Celsius. So very simple. I'm going to go ahead, I'm going to multiply these out. So 100 times 4.186 times 50. And what I should get for my Q is 20930 joules. So that is what I would have on there. So that is it for topics overall. I would say just make sure that for convection, conduction, and radiation, you guys look over examples on how these things apply on Earth, right? And how those things work coherently. Be ready to do a few of these calculations and be ready to deal with atoms and the covalent bonding and some of the things that we've done this semester. So thank you very much and good luck on your final.